Friends, welcome back to my YouTube channel, and in this class I am going to discuss about the Kelvin-Planck statement of second law of thermodynamics, and also the concept of heat engine will be discussed. In the last class I had discussed about the introduction to second law of thermodynamics, why second law of thermodynamics is called a directional law, and what are other features of the second law of thermodynamics, how it distinguishes between the low grade energy and the high grade energy. So these things were discussed in my earlier lecture. Before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. So let's get started. First, we must know what is a thermal energy reservoir, or simply thermal reservoir, or simply reservoir you may call. So, why will we study this before studying the concept of heat engine? Because it is very important to know what is a thermal energy reservoir. So first we must study what is thermal energy reservoir. Because to study the concept of heat engine, we must know what is a thermal energy reservoir. So, you see, it is actually a hypothetical body with a relatively large thermal energy capacity. It is actually a hypothetical body with a relatively large thermal energy capacity. What is thermal energy capacity? Thermal energy capacity is nothing but product of mass and specific heat of the substance. Mass and specific heat. If you multiply mass with specific heat of a particular substance, you will find the thermal energy capacity, or it is also called thermal mass also. Thermal energy capacity or thermal mass. So, in fact, the reservoir is a body with a relatively large thermal energy capacity. इसका जो thermal energy capacity है, product of mass and specific heat है, relatively large है, and that can supply or absorb finite amounts of heat without undergoing any change in temperature. We know that whenever we remove heat from a body, its temperature goes down or decreases. And if we supply heat to a body, its temperature increases. But in case of thermal energy reservoirs, no such thing occurs. Whenever you remove heat from a thermal energy reservoir, its temperature neither goes down, and whenever you supply heat to a reservoir, its temperature does not rise. That's the difference between any other body and thermal energy reservoir. In practice, what happens? Large bodies of water such as river, lake, oceans, all can be considered as a thermal energy reservoirs. And apart from that, atmosphere can also be considered as a reservoir. Atmosphere can be considered as a reservoir. Why? Suppose in case of power plants, what happens? When the waste energy is dumped into large water bodies, maybe a river or lake or ocean, or into atmosphere, its temperature does not go up. Even in winter, the heat dissipated by large buildings does not cause any rise in the temperature of atmospheric air. So that's why the atmosphere can be considered as a reservoir, thermal energy reservoir, because it can absorb large amount of heat. Without having any increase in its temperature. So atmosphere can be considered as a low temperature reservoir because it can absorb a large amount of heat. And on the other hand, what can be your high temperature reservoir? High temperature reservoir can be furnace, in industrial furnace, solar energy, nuclear reactor, these things can be high temperature reservoirs. So in fact, in some books you will find that they have written like this: thermal energy reservoir is a body of infinite heat capacity, but it is not precise to term it infinite. These are in fact not the bodies with infinite heat capacity, but they are having relatively large thermal capacity. You can say they are not very large or infinite bodies. They are not very large or infinite or bodies with infinite heat capacity. As some books, you will find that the definition of thermal energy reservoir, that infinite heat capacity. This is not actually true. They may be having high thermal capacity. Thermal capacity is nothing but product of mass and specific heat, and they may be having relatively high thermal capacity relative to the amount of energy they absorb or supply. That means, so that there would be no change in their temperature. So I can write like this: they are large bodies with high thermal capacity relative to the amount of energy they supply or absorb. So whenever they absorb or supply heat, there will not be any change in temperature, because their thermal capacity is relatively large as compared to other bodies. For example, in case of a room, you see there may be some heat dissipation from TV sets, but that heat dissipated from the TV set is not able to cause any rise in the temperature of the air inside the room. In that case, you will consider air inside the room as a thermal energy reservoir. That means the air inside a small room can be a reservoir whenever we are analyzing the TV set, the heat dissipation from TV set. But in the same room, if we consider a room heater, and some electrical current is given to it, and heat is dissipated to the room, and by that heat the temperature of room air goes up. In that case, room air cannot be considered as a reservoir, because there is a rise in temperature. So with respect to that big amount of heat that is dissipated from room heater, the temperature of room air is increased. So that in that case, the room air cannot be considered as a reservoir. On the other hand, it can be considered as a reservoir whenever we are analyzing the heat dissipated from TV sets, because that heat dissipated from the TV sets is not that large. So it is a relative term. You can define thermal energy reservoir as a body of infinite heat capacity. That is not true. So in fact, another example of reservoir can be two-phase system. That means a mixture of solid and liquid. Whenever a solid absorbs latent heat of fusion, it is converted into liquid, and whenever a liquid absorbs latent heat of vaporization, it is converted into vapor. In that case, two-phase system can be considered as a reservoir, because they can absorb a large amount of heat without undergoing any change in temperature, because the temperature remains constant during that process of phase change. So that two-phase systems, either solid liquid mixture or liquid plus vapor mixture, can be considered as a reservoir. So this is all about thermal energy reservoirs. And a reservoir that supplies energy in the form of heat is called a source. That is called a source, which can absorb heat, which can supply energy in the form of heat. And one that absorbs energy in the form of heat is called sink. So there are two terms generally used in case of a concept of heat engine. So source and sink. Source is the high temperature reservoir from which heat can be released, and sink is the low temperature reservoir to which heat can be given. Or sink can absorb heat and source can supply heat. So next is the concept of heat engine. Heat engine. You see, heat engine is a cyclic. We have already discussed in just my last video that second law distinguishes between heat and work. Work is said to be a high grade energy because the complete conversion of work to heat is possible. No such special device is required. Complete and direct conversion from work to heat is possible. On the other hand, the complete and direct conversion of heat into work is not possible. And for that conversion to take place, we need some special devices which are called heat engine. So heat engine is a cyclic device. That converts a fraction of heat input to net work output. In fact, cycle here refers to thermodynamic cycle. Heat engine is a cyclic device that converts a fraction of heat input to net work output. क्योंकि हमको पता है कि heat cannot be completely converted into work. So some fraction of heat can be converted, and that too, for that conversion we need some special devices which are called heat engine. So heat engine is a cyclic device that converts a fraction of heat input to net work output. So what are the examples of heat engine? You see, steam power plant, where there are four components. You will study in detail while studying vapor power cycle. Steam power plant, where there are four components like boiler, turbine, condenser and pump. So there is certain heat input, and out of that some work is produced in turbine, and out of that some part of produced work is consumed when we are compressing the water from condenser to pump. So that means steam power plant is a heat engine because fraction of heat supplied is converted into net work output. But strictly speaking, certain other devices like your IC engine, internal combustion engine, and gas turbine, people may call it heat engines, but they don't fit to the definition completely, because in case of internal combustion engine means the combustion here takes place inside the engine, and also gas turbine is the same with the gas turbine. And in these kind of devices, the working fluid does not complete a cycle, thermodynamic cycle. They may be completing a mechanical cycle, but they don't complete a thermodynamic cycle, because the fuel once burns is exhausted from the engine, and a new fresh fuel enters into the engine. So that means no fluid completes a cyclic process. Cyclic heat engine means the working fluid, the heat is transferred to the working fluid and heat is also removed from the working fluid, and working fluid completes a cycle. That is the cyclic device. Some working fluid is there, जैसे कि स्टीम पावर प्लांट में वाटर इज द वर्किंग फ्लूइड. ऑफ कोर्स फेज चेंज होता है बॉयलर में एंड कंडेंसर में. लिक्विड को वेपर स्टेट को जाता है बॉयलर में, एंड कंडेंसर में वेपर से लिक्विड स्टेट को आता है. लेकिन वही वाटर इज द फ्लूइड, वाटर इज द वर्किंग फ्लूइड इन स्टीम पावर प्लांट. सो in this case, IC engine and gas turbine are not the proper examples of heat engine, but people tend to take them under the heat engines. But they are actually such engines, such devices which don't complete a thermodynamic cycle but mechanical cycle. But the only proper example of heat engine is steam power plant, which are called also external combustion engines, because the combustion takes place outside the system. I will go in detail little while after. So now, but what are the common features of heat engines? You see, first feature is these are four features which are common to every heat engine. They receive heat from a high temperature source. हमेशा एक सोर्स होता है, हाई टेम्परेचर सोर्स होता है जहाँ से हीट एनर्जी आता है, जैसे कि सोलर एनर्जी हो, ऑयल फर्नेस हो, न्यूक्लियर रिएक्टर जो हमारा न्यूक्लियर पावर प्लांट में होता है, ये सोर्स है. और थर्मल पावर प्लांट में ऑयल फर्नेस होता है. कोल से भी हीट आता है, कोल बर्निंग से. सो सेकेंड जो एसेंशियल कैरेक्टरिस्टिक्स दैट डिफाइन हीट इंजन इज दे कन्वर्ट पार्ट ऑफ दिस हीट टू वर्क. दैट इज इंपॉर्टेंट. नॉट heat cannot be converted 100% to work, because some fraction of heat is converted. Not all the heat that comes can be converted to work output, and they reject the remaining waste heat to a low temperature sink. Whatever, suppose Q1 हीट आता है, उससे हम अगर W नेट वर्क प्रोड्यूस करते हैं, तो Q2 अगर वेस्ट हो जाता है तो हमारा ये वेस्टेज हो गया. Q2 वेस्टेज हीट, Q1 कैनॉट बी कंप्लीटली कन्वर्टेड इनटू नेट वर्क आउटपुट. सो दे रिजेक्ट द रिमेनिंग वेस्ट हीट टू ए लो टेम्परेचर सिंक, जैसे कि एटमॉस्फेयर हो, रिवर्स हो, and they operate on a cycle. Every heat engine must operate on a cycle, means thermodynamic cycle. So अगर हम इसको जाएंगे, इसका फिगर ऐसे होगा. ये है हाई टेम्परेचर सोर्स. यहाँ हाई टेम्परेचर सोर्स, यहाँ से हीट आता है Q इन, और ये हीट इंजन साइकिल कंप्लीट करता है. दीज आर पावर प्रोड्यूसिंग साइकिल, सो क्लॉकवाइज. एंड यार नेटवर्क आउटपुट ये प्रोड्यूस होता है एंड ये हीट सप्लाइड होता है. लेकिन क्यू इन से क्यू आउट बाहर जाता है. सो ऑल द हीट दैट कम्स इनटू द सिस्टम, दैट इज क्यू इन, कैनॉट बी कंप्लीटली कन्वर्टेड इनटू डब्ल्यू नेट आउट. सम पार्ट ऑफ क्यू इन विल बी वेस्टेड, दैट इज क्यू आउट, जो कि वेस्ट होने के बाद वो लो टेम्परेचर सिंक को जाता है. ये कंप्लीटली वेस्टेज है. There is no such device that can completely convert this heat input into work output. There will always be some heat rejection. That's why the efficiency of heat engine cannot be 100%. So part of the heat received by a heat engine is converted to work, while the rest is rejected to a sink. So अगर हम स्टीम पावर प्लांट का स्कीमेटिक डायग्राम को देखेंगे, ये ऐसा है. यहाँ suppose this is a steam power plant. यहाँ फर्नेस में फ्यूल बर्निंग होने के कारण हीट प्रोड्यूस होता है. Chemical energy of fuel is converted into heat energy. That heat energy enters into a boiler where water here enters into boiler, and after receiving this heat input, phase change of water takes place and liquid water is converted into vapor state. And sometimes also superheater is there, which brings the steam into superheated state. We will study that in detail in power plant engineering. And once the phase change of water takes place, then it expands in the steam expands in the turbine, and some mechanical work is produced. Later on it is converted to electrical energy through generator. That is a different thing. But here the conversion of enthalpy into kinetic energy takes place, as we have already studied in steady flow energy equation for turbine. Then it comes to the condenser, where again phase change takes place. Here the steam is converted into saturated liquid, and some heat is rejected in the process, and that heat will go to the energy sink such as atmosphere, and then the liquid water is pumped or compressed to the boiler pressure. Here this is a low pressure line and this is a high pressure line, so some work is consumed in pump. Whatever work is produced in this W out of that some work is consumed in pump. Actually this work is quite negligible as compared to W out. W in is quite negligible to W out in case of a steam power plant. Otherwise there is no meaning of this running of heat engine. So significant amount of work output is there. Out of that some amount of work is consumed in the pump, and this is the heat supplied, and this whole system can be considered to a closed system because there is no mass. Whatever mass here enters, this mass circulates and completes a cycle. So this working fluid here is water, and water completes a cycle, and during some part of operation, that is here, heat is added to the water, and here heat is rejected from the condenser. But this whole system can be considered as closed because there is no mass interaction taking place between surroundings and system. This is in the surrounding, this is in the surrounding, and this box is the your system boundary, and this whole system can be considered to be a closed system because in closed system there is no mass interaction. Here energy interaction are there. Q in is here, W out is here, Q out is going outside, W in is work is coming in. So these are energy interactions just taking place. But if you go to individual components like turbine itself can be considered as an open system because here mass of steam enters into turbine and certain mass of steam leaves. So that's why this turbine, the individual component of turbine can be considered as an open system. Condenser can also be considered as an open system, and steady flow energy equation can be derived for every component, that is pump, boiler, turbine and condenser. But as a combination, this combinations of these components is a closed system because there is only energy interaction between this closed system and the surroundings. So here the net work output will be W out minus W in, because this is net work output. So here is the representation. Here it is a heat engine, same heat engine, that is steam power plant. W out is the work output, and work in is consumed out of this net work output. So net out, this W net out will be nothing but W out minus W in. यहाँ total work जो produce होता है, shaft work, rotating in the form of rotating shaft, some work is produced in case of turbine, and that W out of that W out, certain W in is consumed in the pump. So whatever remains, that is W net output. Net output is W out minus W in. And in terms of heat also, this net work output can be calculated. In terms of heat also, that net work output can be calculated. So W net we found out is equal to W out minus W in. Oh, this is also equal to Q in minus Q out. Q in minus Q out. क्योंकि according to first law of thermodynamics, for a closed system undergoing a cyclic process, sigma W cycle is equal to sigma Q cycle. क्योंकि हमारा जो ये इक्वेशन है Q is equal to delta U plus W, and for a cycle undergone by a closed system, delta U will be 0, because cyclic integral of any property is 0, because the system comes back to initial state. The final state is identical with the initial state, so change in any property is 0. So at that time sigma Q becomes sigma W. So net work output will be net heat input. Net heat input मतलब यहाँ Q in आता है और Q out बाहर जाता है. So net heat output will be Q in minus Q out. Net heat input will be Q in minus Q out, and so that is same as W out minus W in or Q in minus Q out. यहाँ से हम efficiency निकाल सकते हैं. Efficiency, thermal efficiency to be precise, thermal efficiency, which is usually denoted by this. So thermal efficiency is nothing but any heat engine is W net output divided by heat supplied, Q in heat supply. यहाँ net output, यहाँ W net output, W out minus W in or Q in minus Q out, and divided by Q in, because we know that no heat engine can be 100% efficient, because all the heat supplied to a heat engine, that is Q in, cannot be converted into W out. Some Q out term will be there, some heat is here rejected in the condenser. So that's why thermal efficiency will be W net output divided by Q in, and I can write this Q in minus Q out divided by Q in, and I can write like this Q in by Q in minus Q out divided by Q in is equal to 1 minus Q out divided by Q in. In all the energy, 4 terms of energy interactions, that is Q in, Q out, W out and W in, are positive quantities. So that's why efficiency of this term will be positive. That means thermal efficiency of any heat engine is always less than 1 or 100%. किसी भी हीट इंजन का थर्मल एफिशिएंसी 100% हो नहीं सकता है. It will be definitely less than 1 or 100%, क्योंकि the complete conversion of heat into work in a cycle is impossible, as is told by second law of thermodynamics. So this is less than 100%. Some Q out term will be there. There will be some wastage of heat energy. So thermal efficiency is actually a measure of thermal efficiency of a heat engine. Thermal efficiency of heat engine is a measure of performance of heat engine. It describes the fraction of heat input that is converted to net work output. ये नेट वर्क आउटपुट टर्म क्यों यूज होता है? क्योंकि डब्ल्यू आउट तो होता है टरबाइन में, लेकिन कुछ वर्क पंप में कंज्यूम हो जाता है. टरबाइन इज ए पावर प्रोड्यूसिंग मशीन, whereas pump and compressor are work consuming machines, and in fact for compressing liquid we need pumps, and compressing gases we need compressors. So that's why here you will be having the pumps. So thermal efficiency is actually a measure of performance of heat engine, and you must remember one thing, it is always less than 100% or 1. In percentage terms, it will be always less than 100%, and to be precise, for SI engines, the thermal efficiency, SI engines, spark ignition engine or petrol engines, this thermal efficiency is of the order of 25%. Is of order of 25%. And for diesel engines, diesel engines matlab compression ignition engines, the thermal efficiency is of the order of 40%. And for combined gas steam power plant, efficiencies may be around 60%. So nowhere efficiency is near 100%. So 100%, this limitation on the efficiency, this limitation on the efficiency of heat engine being 100% is not due to friction effects. One thing you must remember, this nowhere the heat efficiency of heat engine can be 100%, but that limitation is not imposed by dissipative effects, not due to friction and dissipative effects. ये dissipative effect के लिए नहीं है, dissipative effects, and this limitation applies for ideal and actualized engines, दोनों के लिए. So this limitation actually forms the basis of Kelvin-Planck statement, and this limitation of the efficiency of any heat engine being less than 100%, or impossibility of efficiency of heat engine being 100%, is the base of the Kelvin-Planck statement of second law. Kelvin-Planck statement. This is Kelvin-Planck statement of second law. Second law of thermodynamics. There are many statements of second law of thermodynamics, but there are mainly two statements which are discussed, that is Kelvin-Planck statement and Clausius statement. So now we'll study Kelvin-Planck statement of second law of thermodynamics, and it says that it is impossible for any device, that operates on a cycle, to receive heat from a single reservoir to produce net work output. So it is impossible for any device that operates on a cycle to receive heat from a single reservoir to produce net work output. So for a heat engine to produce net work in a cyclic process, it has to exchange heat with two reservoirs. One is source and one is sink. If you say it will only interact heat with, suppose there is a source and heat is coming, suppose this is steam power plant, boiler, turbine, condenser, pump. and work is produced, and W net is equal to Q in. Some network output is produced and that is equal to Q in. This is a impossibility. This is not possible. This is not possible, and this device is called, this is in violation of Kelvin-Planck statement. So it has to be a sink. If you eliminate that sink, and this is a machine which violates the Kelvin-Planck statement of second law of thermodynamics, and this is also called perpetual motion machine of second category, which is impossible. And if you calculate the efficiency of this PMM2, it will be 100%, because we know efficiency is equal to net work output divided by Q in. क्योंकि यहाँ कोई भी हीट रिजेक्टेड नहीं हो रहा है, सो Q in इज इक्वल टू W net, मतलब ये 1 हो गया और 100% हो गया. सो ये मतलब PMM2 है और इम्पॉसिबल है. So heat in other words, we can say the Kelvin-Planck statement can be expressed in other words also. So Kelvin-Planck statement can be expressed in other words. No heat engine can be 100% efficient. It can produce some work, useful work, only if it exchanges heat with two reservoirs, that is source and sink. You see, that means in case of a power plant, the working fluid has to exchange heat with two reservoirs. One is furnace and another may be atmosphere or river or any water bodies. That means in boiler, so heat will come from outside, because this is an external combustion engine. Combustion will take place outside that closed system, and that is your source. And from the condenser, some heat will be released to sink. So then only some work output may be produced. Out of that work output, that work produced in the turbine in the form of mechanical work, some part of work is consumed in the pump while compressing, or while compressing the liquid to boiler pressure, so that the cycle will continue. So that's this is Kelvin-Planck statement, and it is actually says one thing, that is no heat engine can be 100% efficient. So that's all. Thanks for watching.